In this recording, we'll go through several conceptual questions. Let's start with this one. Suppose the entire population of the world gathers in one spot and at the sounding of a prearranged signal, everyone jumps up. While all the people are in the air, does the Earth gain momentum in the opposite direction? Okay? Now think of it. This is our Earth, and this is all of us. Okay, so the Earth plus people have a particular momentum at this instant. Now they jump. So all the people are here. So they have a momentum in this direction, a new momentum in this direction. What should happen for conservation momentum? The Earth should have an equal momentum in the opposite direction. Now, it does not matter what the mass of the Earth is, the momentum should be the same. That's conservation momentum. Momentum before is equal to the momentum after. So the Earth is going to recoil like a rifle firing a bullet with a change in momentum equal to and opposite to that of the people. That should be my correct answer. Actually, if you go to NBCnews.com and search for this kind of topic, you should find an article a few years back where in a prearranged signal they had school kids all jump at the same time, and according to what they say, they were able to detect some anomaly in earthquake detection devices that they have there in England. So the jump created enough of a change in momentum that was perceivable by the instruments that they used to detect earthquakes. That's an interesting thing, where they arranged for all school kids to do it at the same time. Now, again, the same question. About a second later, these 5 billion people land back on the ground. After the people have landed, what's the Earth's momentum? The same as what it was before they jumped, different from what it was before the people jumped. Of course, it has to be the same, since we don't have external forces acting on the system made up of the 5 billion people and the Earth. We don't have external forces, so the momentum, the overall momentum should remain the same. So we should go back to what it was before the jump. Now, consider two carts of mass m and mass twice m at rest on an air track. The idea of air track, no friction, like air hockey. If you push the first one for 3 seconds and the other one for the same length of time, exerting equal force on each, same length of time, the momentum of the lighter car is going to be 4 times, twice, equal 1/2 or 1/4 to the momentum of the heavier cart. Okay. Now this is a tricky question because most of us will think of the wrong answer here. I'll let you decide what your choice is, but the initial momentum in both cases is 0. And then what do? We exert an impulse on both of them. What's the impulse? Impulse, change in momentum, but it is also the average net force that we apply times t. And in this case, we have the same force and the same time acting on both of them. If we have the same force and the same time, that means we exert on them the same impulse. It means their change in momentum is the same. And since they started with the same initial momentum, their final momentum should be then the same. And that's my answer. Now, of course, if I ask you which one is going to be moving faster at the end, we answered a similar question before, like with I forget their names, the lady and the man. Of course, the one with the lesser mass is going to be moving faster than the one with the bigger mass, because the one with the lesser mass is going to have a larger acceleration. Okay, a person attempts to knock down a large wooden bowling pin by throwing a ball at it. The person has two balls of equal size and mass, one made of rubber and the other of putty. The rubber ball bounces back while the putty does not. Which ball is most likely to topple the bowling pin? Okay, and that's what we talked about before. If I have something that's with a momentum this way and it bounces back, the impulse on it is twice as much as something that's going to hit like this and stops. So the impulse on it is going to be twice as much, meaning that the impulse it's going to exert on whatever it's going to hit is going to be twice as much. So the one that's going to bounce is going to exert twice as much impulse, meaning it's going to be the one most likely to topple our bowling pin. So the rubber ball is going to be the winner in this case. Okay, is it possible for a system of two objects to have zero total momentum while having a non-zero total kinetic energy? Of course it's possible. Think of this case. If momentum 1 is equal to momentum 2 in magnitude, the overall momentum is P1 plus P2 is 0. But then the kinetic energy is not 0, since kinetic energy, this is, let's call it EK1, EK2. Kinetic energy is going to be EK1 plus EK2. It's going to be something larger than 0, and kinetic energy is always larger than 0. So the answer, yes. Now, is it possible for a system of two objects to have zero total momentum and zero total kinetic energy after colliding if both objects were moving before the collision? Okay. Now it's the same question. We start with zero total momentum, zero total kinetic energy after colliding. That's what they are telling us. Is it possible if they were moving before the collision? Of course, yes. That's an inelastic collision where two objects come, hit each other, and then stop. What's key is momentum is conserved. Momentum is conserved in this case when they stop. Kinetic energy does not have to be conserved. It's an inelastic collision. Okay, a car accelerates from rest. In doing so, the car gains a certain amount of momentum. Okay, remember what makes the car accelerate? A force exerted on it through the tire by the earth. Now, and the earth gains more momentum, the same amount of momentum, less momentum. The answer depends on the interaction between the two. Of course, the question is all the time, if something is going to push something forward, it's going to be pushed in the opposite direction. If it's going to exert an impulse on something, it's going to experience the same impulse in the opposite direction. So now, what that means, the earth is going to gain the same amount of momentum in the opposite direction. A car accelerates from rest. It gains a certain amount of kinetic energy. And the earth, okay, is it going to gain more kinetic energy, same amount of kinetic energy, less kinetic energy, or whatever? Now, of course, here it cannot be the same. Now, they are going to have the same momentum. Momentum of car is going to be equal to momentum of earth in magnitude when we don't worry about direction. Momentum of the car is mass of the car, velocity of the car. Momentum of the earth is mass of the earth, velocity of the earth. Now, think about this. The mass of the car is very small compared to the mass of the earth. The velocity of the car, the velocity that the car gains, is very large compared to the velocity of the earth. notation Hewitt, the way he uses it in his book, he uses MC like this and VC like this. That's equal to ME like this and VE like this. Small, large, large, small, and they are equal to each other. Now, when it comes to kinetic energy, what's kinetic energy of the car? 1/2 of mass car and velocity of the car squared. Now, sorry about that. What's the kinetic energy of the Earth? 1/2 of mass Earth, velocity of the Earth squared. Now notice here, in the case of the kinetic energy of the car, we are squaring the large number, Vc. But for the kinetic energy of the Earth, we are squaring the small number, Ve. Obviously, when we square the large number, we get a bigger number than when we square the small number. So this means that the Earth is going to gain less kinetic energy. Okay, now this other question. 2 marbles, one twice as heavy as the other, are dropped to the ground from the roof of a building. Just before hitting the ground, the heavier marble has as much kinetic energy as the lighter one, twice as much kinetic energy, half as much, 4 times as much, and whatever. Okay, what do we know? We know the balls, the marbles, that when they are going to be about to hit in the ground, if we are ignoring air resistance, they are going to have the same speed, same momentum, same speed. They are not going to have the same momentum because momentum is m times v. So the heavier one is going to have twice the momentum as the lighter one, since it has twice the mass. They have the same speed, same velocity, but the heavier one is going to have twice the momentum. What about the kinetic energy? It's the same speed. The only thing that's going to change is the mass. The only thing that's going to be different is the mass. And the kinetic energy is 1/2 of mv squared. So if I double the mass, I'm going to double the kinetic energy. So I having twice the mass, meaning I will have twice the kinetic energy. So this is my answer.